Hello, EOS110. This is a video about calculating radiation intensity. So when the sun is coming down and not perpendicular to the ground, its rays spread over a larger area. And we want to calculate the reduction in energy due to that spreading over the larger area. So I'm going to start with a diagram and some definitions here. So this horizontal line here is meant to symbolize the ground. And the sun's rays will be coming in to strike the ground at an angle. So this arrow here indicate the sun's rays. Now, I can draw a line here perpendicular to those sun's rays. This would be a right angle here. And what I'm trying to figure out here is actually the ratio of the side A of the triangle to side B here, the hypotenuse. So in the real world, you can picture yourself holding up something flat, perhaps a piece of plywood, so that it's perpendicular to the sun's rays. And the radiation intensity on that piece of plywood would be 100%. The sun is striking there the smallest area that it could. If you take that piece of plywood away, now that same energy is spreading out over a larger area, symbolized here by side B. The ratio of these two sides is related to this angle here, which I'm going to call SA for sun angle. And there's one more angle we need to think about. If I were to go out and plant a perpendicular pole here, so going straight up, then this angle here is the zenith angle. Okay, so let's make a note of all those things. My side A there is perpendicular to the sun's rays. And the energy spreads out on side B. Okay, so side B is the ground in this case. We have our two angles to worry about. The SA is the sun angle, and the Z is the zenith angle. Okay, so as I said, we want to calculate the relationship of A and B to each other. The ratio of them is this radiation intensity that we're after. And it's equal to the sine of that sun angle. Remember, that's the angle between the sun's rays and the ground here. So if we can know what that sun angle is, then we can calculate the radiation intensity. Now there's another relationship here. We can also see that the zenith angle and the sun angle have to add up to 90 degrees because the pole makes a right angle to the ground here. The zenith angle plus the sun angle equal 90 degrees. Now to figure out what that sun angle is, we have one more formula to think about, and it relates the zenith angle to the latitude and the declination angle at noon. So if we're not at noon, we can't use this. We'd have to alter this formula, but at noon, solar noon, that zenith angle is equal to the absolute value of the latitude minus the declination angle. Okay, so Let's do an example to really show how to do a calculation like this. We did one in class for Victoria as our location during the equinox, and I want to do one here in the video for Victoria again because we like Victoria, but at the December solstice. So the example we'll do will be Victoria again. And Victoria has a latitude of 48.4 degrees north. And we're going to do it for the December solstice. So the first thing I'll move to do then is to figure out the zenith angle. That's equal again to the absolute value of the latitude. We just said that should be 48.4 minus my declination angle. Okay, so I got to figure out what the declination angle is for the December solstice. Here's a slide from our lecture where we looked at the declination angle. Remember that the declination angle is the latitude at which the sun is directly overhead. So here, if we look at this diagram, we see on the x-axis different latitudes essentially, and sorry, that is the y-axis, different latitudes, and on the x-axis, different times. So here we can see that this line crosses the equator, 0 degrees, at the equinoxes. So at the equinox, the sun is directly overhead of the equator at noon. In the summer solstice, we can see that it gets to about 23.5 degrees north. And at the winter solstice, which is what we're looking for here, the minimum value is 23.5 degrees south. So that's what we want. We want to use 23.5 degrees south for the December solstice. So I want to put that in as my declination angle. We talked in class that southern latitudes in the southern hemisphere should get a negative sign. So I want to enter here a negative 23.5 degrees. So my zenith angle then is 48.4 degrees minus a negative 23.5 degrees. Or you could change the sign in your head and say this is 48.4 plus 23.5. Okay, so I have 48.4 minus a negative 23.5 gives me 71.9. It's the absolute value of 70.9, but it's already a positive number here. Okay, that's my zenith angle, but remember what I need is my sun angle. And again, we're at noon in this case. So sometimes we call this the NSA for noon sun angle. Equals 90 degrees minus that zenith angle, the noon zenith angle. Okay, so for this case, we have 90 degrees minus 71.9 degrees, that was our zenith angle, is going to give us 90 minus 71.9, 18.1. So that's our noon sun angle on the December solstice here in Victoria. Our final part of this calculation is to calculate the radiation intensity, which is the sine of that 18.1. So sine 18.1, 0.31. And so our radiation intensity is equal to 31% in this example. There you go. I hope that was helpful in learning about radiation intensity.